In this lecture, we're going to talk about the expressive power of GNNs. In essence, we're going to be deep diving this single paper called How Powerful Are Graph Neural Networks? And in that, they use the connection with the Wiesweiler-Leman algorithm to really frame this question and tackle it. And they show that GNNs can be at most as powerful as the 1WL graph isomorphism test. And then they introduce a model that meets this upper bound and is as powerful as 1WL, which they coined the graph isomorphism network, or GIN. There's an entire lecture that is in this course on this topic of the WL algorithm, but as a quick refresher, we give each node in it an initial label, and if nodes have features, you can imagine that it comes from some countable set where each unique feature gets a particular label. We then do the message passing step where each node collects all of its neighbors' labels into this multi-set, which is a set where the same element can occur more than once. And for this, we can construct a tuple for each node where you have the current label and the neighbor multi-set pair, and map that to a new label, which then allows us to partition the graph based on nodes that share the same label. And in essence, what we're doing here is each unique neighborhood is going to get a label, and then additional iterations consider larger and larger neighborhoods. We have a diagram here where we can start out with this small graph. Each node has the same label. On the first iteration of this algorithm, you see that we get two colors, orange and purple. In the case of orange, the multiset here has two nodes that are in the neighborhood multiset. And in the case of purple, there's three nodes. In essence, this color is telling the difference between nodes that have two neighbors and three neighbors, which indicates their color here. And then on the next step, we see a further differentiation, whereas before all four of these nodes had the same color. In this case, we see two yellow, two green, and the real difference is that in the case of yellow, you have one neighbor of degree 3 and one neighbor of degree 2, whereas in the case of green, both neighbors are of degree 3. So we see how this information from further neighborhoods, further hops away, is being incorporated to update these labels and differentiate the nodes. So what's the connection here with GNNs? Well, the core of the WL algorithm is in mapping this multiset that's resulted from this local message passing to the unique label or color. The paper says that we can reduce our analysis to the question of whether a GNN maps two neighborhoods, i.e. two multisets, to the same embedding or representation. Mapping different neighborhoods or multisets to the same output is a failure. That means we have two distinctly different things, but we give the same answer. That means we're not able to distinguish them, and that would be a failure. Limit 2 proves that 1WL is the upper bound of GNNs. And the way they do that is through contradiction. If you suppose GNN A can distinguish between these two graphs, G1 and G2, after k iterations, but you suppose that 1WL is failing and can't, that would imply that 1WL has identical label multisets for each graph. However, A is fundamentally being given these same label multisets as input, because the GNN can be decomposed into this aggregate step, which operates on the collection, the multiset of neighborhood labels to create this neighborhood representation, and then that neighborhood representation is combined with the current node embedding to get a new node embedding through this combine. But if the inputs are the same, which is why 1WL would be failing, the outputs therefore have to be the same, because this is a deterministic function. Which means that if 1WL is failing, the GNN also has to fail. So this is proved by contradiction. Recall that the labels here are referring to unique node identities, which in the case of node features refers to unique node features. And I think that's instructive because it's clear that if you're giving a neural network the same set of inputs, you're of course going to get the same set of outputs. And I think that's enough to see that the 1WL is going to be the upper bound, because by definition it has this hash map where it's mapping unique things to unique outputs. And if you can't do that to distinguish, then your GNN is of course going to fail. So we know that 1WL is going to be the upper bound, but how do we actually get to this upper bound? Well, Theorem 3 shows that if you parameterize your GNN in this way, where you have this function that operates on the neighborhood of multisets, and then this update function, or combine function that they refer to it, as long as your functions f and phi are injective, then you will meet this upper bound. And injective just means that you will map distinct inputs onto distinct outputs, or if you have two different inputs, they never get the same output. In this case, functions mapping distinct multi-sets of node features onto unique embeddings. And this proof is simple in that it just relies on the idea that the composition of injective functions will itself be injective. And to get a GNN as powerful as 1WL, we therefore need injective aggregation function, f, and an injective update function, phi. First, we'll tackle the aggregation function. And to do this, they extend the deep sets work to include multi-sets. Deep sets we've mentioned in a previous lecture, in that they stack these equivariant and invariant operations to create a universal set function approximator. It's equivariant because it's applying the same MLP here to each element in the set. And then the invariance comes from this aggregator. Here it's a sum, but it could be a general aggregator like average or max. And then the result of that passes through a multi-layer perceptron. However, what we want is a universal multi-set function approximator where the same element can occur more than once. In Lemma 5, they show that you can do the same deep set recipe and generalize it to multi-sets if you limit it to the sum aggregator. And I think a simple way to observe this is that if you do a one-hot encoding for each element, each unique element in the set, and then apply the sum aggregator, that's in essence going to count the number of each element. If you imagine, for example, A gets mapped to this first bucket and B to the second, and then you add these two one-hot encoded vectors, you'll get 1 and 1. And if you have two A's and two B's, you'll get 2 and 2. And you can imagine how this will distinguish any multiset that's different, because we have both the identity of each element and the count of each. However, if you were to consider average or max, you would see that those would fail to distinguish these. That in both cases, you're going to get 1, 1 if you were to average this or average this. And similarly with max, you would get 1 and 1. Again, assuming that A and B were one-hot encoded. That's our injective aggregate function. Now we need our injective update function. And that's provided to us by summing the node's previous representation with this neighborhood aggregate that we just calculated. However, they don't just sum them directly, they multiply this by 1 plus a constant. Why do they do this? Well, briefly consider this simple example of H1 being connected to H2. If phi is injective, then H1 with the neighborhood H2 should be different output than H2 connected with the neighborhood of H1. And if you include this constant and do this, where you have H1 here and H2 here, you see that you have this extra constant on the source node here. And if you were to evaluate this the other way around, you have this constant on H2. Now, of course, if epsilon was 0, then both sides would have H1 plus H2, and this would not be injective. But by including this epsilon, we can tell which one of these is the source node or the home node, and which one of these is the neighborhood node. In it, they say that epsilon here can be a constant or be learnable. They claim that it's an irrational number to help aid in the proof, but I don't think that that's fundamental to the results. Finally, they say that they will parameterize phi as an MLP, and that this will actually take the place of both of these functions because the raw features are going to be passed through this to calculate h in the first place. So we end up having this single MLP that's then just going to sum the neighborhoods with the source node, but then have this constant that also adds to the source node. And this is the final layer form of the graph isomorphism network. One thing I thought was really interesting was they showed that one layer perceptrons are not enough for the update equation. A one layer perceptron is just a linear projection followed by the nonlinear activation, and that's just not sufficient because we see that it actually has this very linear behavior. For example, in lemma 7, they show that the sum of these operators can fail to distinguish multisets, which means they're not injective, of course. For example, if you have Wx pass through a ReLU activation, you can imagine these two simple multisets. x1 is 1, 1, 1, x2 is 1, 2. Now, if all of the x elements are positive, then that means that if w is positive, then wx will all be positive. Or if w is negative, all of wx will be negative because all of the x's share the same sign. Let's take these two cases separately. If wx are all negative, ReLU is going to squash everything to 0. So plugging in x1 or x2 is going to give you 0 in both cases. So we have this non-injective behavior. If wx are all greater than 0, then ReLU is not going to do anything. It's just going to return x. We then can factor out the w because it's not going to be impacted by the sum. What we end up seeing is that the results will be identical if the sum of all of the elements is identical. And that would fail in this case because we'd have 1 plus 1 plus 1, and that of course will equal 3, which is also equal to 1 plus 2. So anytime the sum of these multisets was equal, then this would fail and not be injective. The paper also provides some nice simple examples that demonstrate how some of these other aggregation functions can fail. GCN commonly uses mean, and GraphSage has used max pooling, and these are both permutation invariant aggregation functions, which we need for our message passing GNNs. However, they're not injective for some simple examples, and therefore will not be as powerful as 1WL. This first example shows a node with 2 neighbors and a node with 3 neighbors, all of which are the same label, and mean and max will both fail in that case. They'll give you the same answer for all of these because the mean of whatever number this corresponds to will be the same whether there's two of them or 3 of them because they're all identical, and likewise for max. In the second case, the max will fail, but the mean will not. The max fails because either green is greater than red or red is greater than green, and it doesn't matter how many of each there are. Mean works, however, because the proportion of green to red is different, and it'll therefore be able to distinguish whether there's 1 to 1 or 2 to 1. That'll result in different means. And in this third case, mean and max both fail again. Here, for the same reason, max doesn't care about the multiplicity of green or red. One of them will be the max. And for mean, the proportions are identical, that there's 1 red and 1 green, and here there's 2 red and 2 green, but again, the same proportion of red to green. The mean aggregator is essentially mapping the same feature distributions to the same output. So whenever you have the same composition of distribution of labels, then you're going to have something that's not injective. It's therefore sensitive to just the relative proportion of red and green, but not to the raw counts. And this might be enough for node classification tasks, for example. They mention this in the paper, where the neighborhood composition is important, but perhaps not the raw counts. And this will just depend on your particular task. But for example, in the context of fraud detection, what might matter more is, do you have more fraud neighbors or more not fraud neighbors? And the raw counts may be less important than the answer to that question. And this doesn't capture the raw structural information, which is likely important for things like graph classification tasks. The max aggregator is interesting in that it essentially ignores the multiplicity and reduces the multiset to just a plain set. This won't capture the raw structural information or the distribution of features, but it will capture information about representative elements. Maybe you have something about celebrity, and if you're connected to a celebrity, that tells you all you need to know about the problem. If instead of node-level representations we want a graph-level representation, then we need some way of combining these node embeddings to get a graph embedding. They call this a readout function, and this operates on the multiset of node embeddings. And of course, for this to be as powerful as 1WL, then it's required that this readout function be injective. They propose, once again, to use the sum. But more than that, they say that at a given layer, K, they want to sum all the node embeddings to get the graph level representation for that layer. That's their injective readout function. But if you have a multi-layer model, then they want to concatenate the representations at each layer, meaning that at each layer you sum up all of the nodes embeddings to get the representation, and then you do that again for the next layer and again for the next layer, and then you concatenate all of those results together. And in that way, your model can see information from different stages of the graph coarsening, different amounts of receptive field of this aggregation. They then go on to do some experiments where they focus on using non-informative features and graph classification tasks. The idea being that they're wanting to evaluate the ability of the model to really capture and represent graph structure and not rely on these meaningful node features. Capacity is then measured on the ability of the model to fit on the training data. And then they separately look at the generalization ability of the method by considering performance on a holdout test set. So first, this question of capacity and fitting the training data. They have a number of different data sets. The first thing we notice is that if you use something based on the 1WL test directly, that this is the upper bound. None of the methods will exceed that. And the ability, here we have something less than 100%, and it's still the upper bound. Nothing is exceeding it. The other thing you see is that this orange and red are both significantly outperforming on some of these data sets and are basically identical with one another. The difference here is whether they use this constant or just set it equal to 0. I think from this we can learn that this constant actually isn't doing anything that important, at least in these data sets. The next thing I thought was striking was the gap between this and the dotted line here, which represents using the one-layer perceptron instead of the multi-layer perceptron. That gives quite a significant boost in performance in this case, and in others. We then see that the sum aggregator is better than the mean aggregator, which is better than the max aggregator in terms of capacity of fitting the training data. And this is all consistent, of course, with the theory that's been worked through so far. As mentioned, they then test the generalization ability by looking at these methods on the test set. The conclusions are mostly the same, but I think one thing that's interesting is that the GNNs are generalizing better than the 1WL. So although 1WL is the upper bound for fitting the training data, if you are instead looking at generalization ability onto unseen, that these other methods of GNNs can generalize even better. Finally, there's some practical limitations here that should be mentioned. First of all, the proofs rely on the features coming from a countable set. That's what's mapping all of these to this kind of hash table underneath, where every unique thing is getting a unique label through, for example, the one-hot encoding mechanism, but it's not clear what the implications are if you're using continuous features, which is actually fairly common. Maybe there's another way to prove it. I haven't put too much thought into it, but at least in the case of these proofs, they're assuming that the features are countable, which allow them to do this label mapping and make the connection with the WL algorithm. The differences in expressive power for these different aggregators is really a result of them handling multiplicity in different ways, whereas mean is looking at proportions and max just ignores it, and sum is actually counting the multiplicity. But if there's no multiplicity, then deep sets shows that all of these permutation invariant aggregators are satisfying this universal set function approximator thing. So if we have really diverse node features, our multisets are approximated by a set, and all the differences between these aggregators kind of goes away. It's really when you have a lot of multiplicity where these differences start to shine. And it's not clear for a real-life data set where it might fall in this spectrum. It could very well be that your node features are diverse enough that any capacity gains that you might get by using sum are erased because it's just not enough multiplicity to matter. The sum aggregator naturally outputs things from different scales as well, and this could present a problem. So for example, if you have a power law distribution for your node degree, meaning some nodes have many, many connections like the Justin Biebers of the social network, then when you perform this operation and are summing the contributions from orders of magnitude more neighbors, that could cause the scale for that node to blow up relative to the average node in the graph. And as we know, when we're training neural networks, having vastly different scales, numerical scales, can cause problems with the optimization task. Typically, tricks like batch norm and things like that come into play, but it's not clear to me how that interacts with this question of injectiveness and whether this would actually break the injective property of the sum aggregator if we're doing this normalization scheme on top of it, in the same way that average is broken because there are these cases where multiple different multisets can have the same average. So maybe batch norm will do the same thing if done in the context of the sum. And finally, if you just look at the leaderboard on the Open Graph benchmark datasets, GIN gives a modest improvement over GCN in some cases, and in one case, GCN actually outperforms GIN. And I don't know how exhaustive of hyperparameter searches were done and all of that, but I think it shows that while there may be an improvement, it's marginal, and there are other simple things done on the leaderboard that offer much larger improvements. And this might suggest that the model capacity really isn't the bottleneck, at least for these data sets. And there's these other practical challenges that are more important, and other innovations that help with the optimization might actually give you more gains. And lastly, I've just put up a number of references here that you can go through that examine the question of how to go beyond 1WL, for instance, in the case of breaking the limits of message passing GNNs. But then there's another paper that sort of shows that when you do that, it actually does worse than GCN-based architectures on a lot of the benchmarks, and then presents some challenges related to, for example, the scalability of these things. And it's just a kind of overview of this side of the work of people grappling with the expressive power, trying to beat 1WL, and if it's even worth doing in the first place. I hope this makes clear the connection between the WL algorithm and the expressive capacity of GNN and gives you a nice framework for thinking about that.